This topic is electromotive force. It's a very important topic, electromotive force. So first, you need to understand that this is a misnomer. This is a misnomer. What is a misnomer? Misnomer means that this is actually not a force. Electromotive force is not a force. Okay, it's just a name that is given, electromotive force, and there is a reason why it is given this name. But this is not a force. This has a unit of energy. So EMF has a unit of energy. So don't mentally think in the terms of force. Think in the terms of energy and work done. Now, first you need to understand that every cell has an internal resistance. Every cell will have an internal resistance, and that internal resistance will be dependent upon the cell's electrode, electrode, and then it is nature of the electrolyte, dependent upon the nature of the electrolyte. So what is a cell? So in electrolysis you have done that this is a cell. So you will have some electrolyte into it, and there will be two anode and cathode electrodes. Okay, this you have done before. So because of this electrolyte inside, you see, because of this electrolyte, this electrode, and because of this directly proportional to the concentration of the electrolyte, then internal resistance directly proportional to the distance between the electrode. Okay, so for all this reason there will be some internal resistance of the cell. So the resistance offered by the electrolyte of the cell to the flow of current between its electrode is called the internal resistance of the cell, and it depends upon the following factor: nature of the electrolyte, okay, type of the electrolyte, then the distance between the electrode, okay, inversely proportional to the common area of the electrode. So that means electrode that you have inserted into this electrolyte, how big is that electrode, what is the surface area, and so on. Okay, and also it internal resistance increases with the decrease in the temperature of electrolyte. Okay, this is also important. Internal resistance increases with the decrease in the temperature of the electrolyte. So if the temperature decrease, then the concentration of the ions in this electrolyte will also decrease, and so the internal resistance will increase because the charge carrier has decreased. Now because of these reasons there will be internal resistance. Now think about a cell. Think about a cell. A cell will have some internal resistance, and this you write it as small r. Then there's an external resistance. This is written as capital R. This external resistance is the resistance that you have put up externally. It has got nothing to do with the internal resistance. Now, if you consider that the current is flowing in this circuit, if you current is flowing in the circuit, then this current is doing a work. Okay, this current is doing a work across this resistance and also across this resistance. So this current is doing a work across both the resistance, external resistance and internal resistance. So if you consider the total work done by the cell in taking the charge around the circuit, then the total work done will be the work done against the external resistance, this one. So this will become the current times the external resistance, and the work done against this internal resistance as well. So this will become I small r. So this value here, the total work done, this value is called the EMF. This is the EMF of the cell. So your expression would become EMF is equal to I times capital R plus I times small r. Very simple. Now you have set up this circuit. You have set up this circuit, and your objective was to get some current flowing through the external resistance. You see, the internal resistance is not yours. You have not set up the internal resistance. It was there before. So whatever the work done across this internal resistance, this is of no use to you. Is it of any use? No, no use. Because the work done in the internal resistance is of no use to you as a user. And you would only be interested in the work done in the external resistance. Now, work done in the external resistance would depend upon the potential at the terminal of the cell. So these are the two terminals of the cell. Terminal of the cell means the the outside part of the cell. That means that part which does this exclude the external resistance, the internal resistance as well. So this becomes your terminal of the cell. This part to this part, this is your terminal of the cell. So a cell is able to give some potential at its terminal, and only that potential you can expect to be dropped across the resistance, and that will be the work done at this resistance, external resistance. So this potential at the two end of the cell is also called the terminal potential. Terminal potential. Terminal potential is also called the potential difference. We'll discuss it in some time. Potential difference. So effectively your expression would become IR. This value here will be called potential difference. Now, why do you call it potential difference? Is because this is the potential that you are going to get in the external resistance. Okay, this is the potential. If I tell you that the EMF of the cell is 10 volt, that does not mean that in the external circuit also you are going to get 10 volt. EMF means 10 volt means that the maximum work that this cell can do in the external and in the internal, both combined, that will be is equal to 10 volt. But what is the potential drop you are going to get in the external circuit will be called the potential difference. And potential difference is simply written as V. So effectively your expression will become E is equal to V, that is this value is the potential difference, the work done in the external circuit, plus I small r, or your expression will become V is equal to E minus IR. And it is very logical also, because you see what is this value? This is the potential drop in the external resistance, or the work done by the cell in the external resistance. This is the total work a cell can do. Total work the cell can do, that is the EMF. And this will be the work done in the internal resistance. So the external work done or external potential drop will be the difference between the EMF, that is the maximum work a cell can do, minus the internal potential drop. V is equal to E minus IR. Now, if V is equal to E minus IR, then you can further on write this IR, write this expression according to the Ohm's law as well. So you know I, you can take it as a common from the very first expression. So V is equal to IR. This is the external work done or external potential drop. And V dash is equal to I times small r. This is the internal work done or internal potential drop. Your total EMF was the sum of these two. So you can take I as a common. So you will get that the current which is flowing in the circuit is equal to the EMF divided by capital R minus small r. Very simple. Now, V potential drop in the external circuit is equal to the current times the resistance, external resistance. Now, just now you have found out the current which is flowing in the circuit, E divided by R, capital R minus small r. So you can then write this same expression as E divided by capital plus small r and into again R. So you can get this value as well. Okay, you can get this value as well. And also you can get that the external potential drop is equal to this minus this and this value as well. So these are the very simple expression that you can get. Further, you can also add on to this expression to get these two expressions as well. You can get these two expressions as well. That is small r is equal to E minus V by I, and then I can be written as V by R. Potential drop in the external potential drop in the external resistance divided by the external resistance itself. So you'll get the current, and then your expression will be E minus V by V into R. So all these expressions are very, very important. You will get quite a lot of numerical based upon this formula and this one. Now we'll discuss about the special cases. The special cases are the one when first case is when the current is not flowing. Okay, when the current is not flowing. Now when does the current not flow? When the circuit is open. In a closed circuit, current will flow, but in an open circuit, current will not flow. So when the cell is an open circuit, that is the current is equal to zero. You see, if the current itself is not flowing in the circuit, then there is no potential drop in the internal or the external resistance. So if this is your circuit, it is an open circuit, as you can see. This is the internal resistance, this is the external resistance. So if there is no current which is flowing in the circuit, then no work is done across any resistance. Then in that case, V is equal to E minus IR. So this value here becomes, whole value becomes zero. So you will get potential drop is equal to the EMF. Thus, the potential difference across the terminal of the cell is equal to the EMF when no current is being drawn from the cell. That is the first condition. The second condition is, that when the current is flowing. So when the current is flowing, your expression will be E minus IR. That is E is equal to V plus IR. That means the EMF will always be more than the potential difference, because a real cell always have some internal resistance R. So when a current is being drawn from the cell, then the EMF will always be more than the potential difference. The third condition will be charging condition. The third condition is the charging condition. Now, what is a charging condition? For example, let's say if you have a cell, with some internal resistance. Now, in this case, if you want to charge the cell, we have discussed this in electrostatics as well, that if we want to transfer the energy to any device, we would have to transfer some charge to the device, isn't it? We have discussed it. So if you want to transfer the energy to the cell while charging the cell, that means you have to give some energy to the cell and you have to give some charge to the cell. That means then the direction of the current will be different. This is the direction of the current when in the charging condition. This is the direction of the current in the charging condition. And then you will have to give potential difference. The potential difference, that is V, has to be more than the EMF. See, you already know that the charges are going to flow from the higher potential to the lower potential. This is the basic concept. Now, if you want the charge to flow to this, cell, that means you have to give the external potential difference should be more than the EMF of the cell. If the EMF of the cell is 5 volt and if you give externally 10 volt, then only the charges are going to flow. If you give externally 2 volt, obviously charges is not going to flow and the cell is going to discharge. So in the charging condition, the external potential difference that you give to the cell should be more than the EMF of the cell. Okay. So these are the three conditions. When the open circuit, the EMF and the volt potential difference is same. In a closed circuit, discharging circuit, EMF is more. And in a charging condition, the potential difference is going to be more than the EMF.